Okay. Slide có di chuyển đúng không?
Dạ có.
Vâng, có di chuyển ạ.
Đấy, hôm nay chia sẻ chỉ có một, không phải toàn màn hình nhé, nó vẫn được ấy. Hôm trước không hiểu sao nó lại bị thế.
Thì nếu cô chia sẻ đúng cái window thuyết trình thì nó sẽ di chuyển được. Còn nếu cô chia sẻ cái PowerPoint thì nó sẽ bị dính ở cái màn hình PowerPoint, nó không chuyển.
Không hiểu. Hôm trước làm giống thế mà. Ok, rồi anyway. Okay, so previous class we have been working with Geoff Fincherson, the principle, and how to work properly with that kind of chromatography column. Okay, so you have already know the represent example for this kind of job function and the application. For instance, in this case, we will determine the oligomerization state of the protein. Okay. Or in another case, here is also kind of a typical example of using job function. The fractionation of complex make up molecule with very close KAV. For instance, in the case you make the digestion using protein. For instance, in the case you use a trypsin digestion for protein, so it will resulting in many small molecule of the polypeptide. Okay, so we need to determine the molecular mass of those polypeptide. Okay, or in the case the second case, the other case is also can be applied Joule function to determine the molecular mass of a typical protein. Yes, to see if this protein in the native or denatured form. Okay, and if in the case that protein is highly reproducible, or if it exists with the long lifespan or not. Okay, so you can characterize this property of a protein. Okay, for instance, if in the case your protein will be eluted with a certain elution volume, right? And you can determine it with the high reproducible. So it means that this protein will be in the native form and is not be denatured, right? So if when you run gel filtration and your protein is be denatured, so it may be in the aggregate form. So in the elution profile, you may obtain not a very nice peak. Okay, and sometimes you cannot obtain or reproduce this protein. Okay, or sometimes when you keep your protein for a time, but it will be degrade. Okay, and then you run again by using your filtration, and you recognize that your protein will be degrade in two small fragments because you will obtain another peak, two separate peak, for instance, instead of one homogeneous peak compared to previous one. So it means that that protein cannot be exist with the long lifespan. Okay. Of course, to determine that, firstly you have to make the calibration. Okay. And the rain normally will work with proteins will be formed belong to this rain. And the determination of mass distribution of polymer is also one of the big applications of the geofiltration. Okay, and determination of equilibrium constant sometimes also can be the application of geofiltration. For instance, for the low reaction or the reactant and the product have to be separate. Okay, so you can put between the two compounds to see to determine the equilibrium constant. It also can be determined by geofiltration, but only for the slow reaction. And geofiltration also can be used to separate a cell and particle. Okay, for instance, you can use the big column to separate the big particle like adenovirus, okay, or poliovirus or lymphocyte, monocyte, okay, etc. So it's also is the good application for geofiltration. Among the advantages of side exclusion chromatography, we know that it can consider as the ideal method for preparing and purification of molecules of different molecular mass of size. So we already know that. Beside that, you know that there the other advantage. For instance, here you have the first point. The retention of the molecule is rather independent of the media. Okay, because we know that the particle, the compound in which we use is the very good compound, so it will not be interfered by the buffer ion exchange, pH, and the temperature. Okay, so the separation can be performed under the best condition for the compound. Okay, in the column. So that is the one of the first advantage of using side exclusion chromatography or geofiltration. And of course, thanks to the property of the gel, the composition of the gel, so there is no or very weak absorption. Okay, so you see sometimes you see the abnormal KAV if there's an absorption of the protein with the gel particle. Okay, but normally there is no or very weak absorption. Okay, but sometimes it happen in with the a special case of very special protein, or sometimes when you use a detergent for the protein, and it easily shift from the analytical to preparative process. Okay, this one. For instance, after you determine the elution volume of a certain protein, you use very like a small column, and you know that with this kind of column, you can make the very well separation between the two protein. Okay, with very small amount. Okay, so it will be at the analytical level. Okay, so it will be easy to see from analytical to the preparative level. Okay, by using like bigger column, same kind of column, but we can use the bigger one. Okay, so that we also can load with the high amount of sample, and we also can separate the two molecule. Okay, so you see the two peak is still well separated. Okay, and for the next point, uh, you already know that this method is also is the method of choice for discounting biological solution. Okay, so this one instead of using dialysis, so you can use cyclone chromatography as the method of choice for this discounting. Okay, so shown is the small molecule, so it will go out at the end of the column after your protein. Okay, so sometimes you can see the effect of SDS if this compound present in the your filtration. Okay, so SDS is the denaturing agent for protein purification. Okay, this one you will use in SDS page, right? You will use in protein membrane. So the completion of SDS with protein is when resulting in denaturation and increase the mass of protein also. Okay, so if in the case in your sample is present at yes, okay, so you can see that the molecular mass can be increased by double. Okay, so without SDS, so you can obtain the peak like that. Sorry, without SDS, you can obtain the peak in the red color like that. Okay, so with SDS, so you will see the molecular mass will be increased in green like that. So pay attention for the effect of the SDS. Okay, so the cause of that is because here in the case you have native protein, right? And when your protein make complex with SDS, so the SDS is will be bound around your polypeptide molecule, so it will denature your protein. Okay, so the mobility of the complex is also depend on the shape of the molecule. And for the normal globular protein, it will move faster through a gel than its linear molecule. Okay, so that reason why you can obtain this one in a different elution volume. Okay, the you also can link that with the migration of the plasmid in the agrogel. Okay, so you can see that with different form of plasmid. For instance, you know that for the relaxed form of the plasmid, okay, for the sugar form or relaxed form, and the other form of plasmid at the hypercoil form, okay, or when you use an enzyme and you cut plasmid at a certain point, okay, for instance this point, so the relaxed forms will become the linear form. Okay, and when you run the this plasmid on the agrogel, you also can see the migration of the molecule at the different speed, different level. Okay, for the same plasmid, here is the position for the relaxed form. Okay, if it in the supercoil form, it will move faster. Okay, and when it is in the linear form. Okay, so normally, for instance, if you have the marker somewhere here, so the marker normally is also in the linear form. Okay, so normally we can determine the correct sign of the plasmid in the linear form. Okay, because the letter is also in the linear form, right? So you can see between the denatured form and the native form, the mobility is, of course, is will be a difference. Okay, so we have done with the first chromatographic purification method, the one very important. Okay, so tomorrow when you present the paper, you will be able to explain the result. You can be able to analyze the result. For the second chromatographic purification method, you have reverse phase. Okay, so hope that today we will finish with reverse phase and maybe ion exchange. Okay. Okay, so for general principle of chromatography concerning reverse phase, so firstly we will see here's the biomolecule, right? So normally every molecule will contain different organic function, different organic group, right? So we will see uh, here, for instance, in the red circle here, you will have the part with the polar group, okay? The hydrogen, the OH, or this group, oxygen only, right? Or you may have the non-polar one containing the aromatic ring here, or you will have the part with hydrogen carbon, right? Aliphatic hydrocarbon. So this part in green is belong to the nonpolar. Okay, so you already know that for the polar group, right? So it will exhibit the hydrophilic property. Okay, so for nonpolar, is this group it intend to away from water. It had water. So the nonpolar group is will exhibit the hydrophobic characteristic. Okay, right? And beside polar and nonpolar ionic function, you also have the ionic group. Okay, so it will create the ionic interaction, right? So based on the different property of those organic function, so we will create different chromatography method, right? And for biochromatography method is also. Okay, so different organic function of the molecule will interact differently with various other organic function, right? Of course. So you have hydrogen bond, ionic interaction, right? Van der between the complementary group, right? And you will have hydrophilic region. We intend to interact with a hydrophilic entity, and the hydrophobic region will interact with the hydrophobic entity, right? Okay, so that is the general property of the organic group. So, a different molecule will show a particular affinity for various chemical compound. And this kind of affinity for this molecule will be specific with the certain support. Okay. For instance, in the case we use thin layer chromatography or TLC. Okay. So you will have kind of aluminum foil, and then this one will be coated with the thin layer of silica. Okay, so it will be coated with the SeO2. Okay, silica, and this silica have very special property. Okay, so you will see that here's the structure of silica molecule, and of course it will have a strong ability to form the polar and hydrogen bond. Okay, right? So that reason why when you coated the aluminum foil with this kind of compound, so it can attack or it can make the interaction with the other compound to create the polar and hydrogen bond. Okay. For instance, uh, for we, do you remember you have kind of paper chromatography in practical course for the first year at US State, right? So you have a kind of practical something like this, okay, right?
I think it's the second year. Yes, but yes.
Okay, no, it's not second year. Actually, it's
I
in
think
your
it's from
first year.
the bioanalytical chemistry practical class, I suppose.
Yes, no, practical chemistry in the first years. You
Also,
will,
I've done it twice.
yeah, no. Actually, for the first year, you perform the paper chromatography. It's not thin layer. Okay, so if in the second year, so maybe you perform exactly thin layer chromatography. In the at the first year, in the first year, you only perform the paper chromatography, but the principle is also like this. And the let's say the stationary phase is a little bit different. You instead of using aluminum foil, you use only kind of paper foil. Okay. Okay. For the first year, you use the color paint, right? And then you make different spot. Do you remember? And then it migrate. Okay. So I think for the next slide you won't be able to remember. Okay. So you will see, for instance, in the case you have the image on the left here. Okay, so the principle of thin layer chromatography have been described as this picture. You will have the first this we call a beaker, okay, or the container. So this beaker will contain the solvent, okay, and then you will put here in the square shape here. So you have this aluminum foil, and it will be coated with the uh, SiO, SiO2. Okay, so this when you deposit the sample right here, so it will be above the solvent level. Okay, in the beaker you will put the solvent. Okay, so when the solvent move migrate here along with the aluminum foil, so the sample can be separate along the movement of the solvent. Okay, so that is how the thin layer chromatography will be performed. Okay, and of course, on the top of the beaker of the container, normally we will cover this here on the top to avoid the evaporate. Okay, okay. So here in another way, when we describe it after you make the run, after you finish the migration, okay. So you will see here is the aluminum foil, right? So the compound to be separate, we will put a zip point, and after you see the migration of the solvent, so your sample can be separate. Okay. And you will have the thin layer chromatography plate here. This one have been coated with silica gel is called stationary phase. Okay, and the solvent in the container, so we call it the mobile phase. Okay, and the compound to be separate, normally it will be above the level of the solvent. Okay, or above the solvent level. Or in another way, when it let the aluminum foil lay down. Okay, so you will deposit your sample here. Okay, so this point in will be the maximum level of the solvent migration, or you will call the solvent front. Okay, so it means that before migration, you will put this foil at this position. This one will be put deeply in the solvent, right, at this point. Okay, yeah, and then the migration will be in this direction, right? Okay, so and then along with the migration of the solvent, so the sample will be separate. Okay, so of course the solvent you will determine the deposit point and the solvent front. Okay, or we can describe in another slide. So you see here you have the deposit point for your sample, right? Here's the initial molecule will interact with the silica, right? Because you have the aluminum foil when coated with silica, right? So at this point, when you deposit your sample will interact with the silica, right? So then you will put the foil into the solvent, right? So here you have the solvent in blue, right? And the molecule, the sample in red, right? So when the solvent molecule slips on the silica surface, okay, so it will interfere the interaction between this sample, the molecule, with the silica interaction. Okay, it's complete though this interaction, right? So if the molecule silica interaction bigger than the solvent molecule interaction, so the molecule stay at the same place, right? Okay, it means that the solvent cannot compete the interaction between molecule and silica, right? But in the case if the molecule silica interaction smaller than the solvent molecule interaction, so the molecule are displaced further. Okay, so it will go further, right? Okay, so here you can see that for you have the deposit point somewhere here. Okay, so the molecule it will be separate according to the interaction with the solvent. Okay, so you will see this molecule in red here is will be molecule with strong interaction with silica, right? And the one move on the top near the solvent front. So this molecule in blue, sorry, in green here, it has a weak or non-interaction or no interaction with silica. Okay, and the molecule in blue and orange, so it will be the molecule with reduce interaction with silica. Okay, so that reason why we can separate those different molecule. Okay, so you can see that the principle of all different kind of biochromatography or chromatography is the compete between different interaction. Okay, so we can calculate the retention factor by distance traveled by the compound divided by the distance traveled by the solvent. Okay. For instance, here you have distance traveled by the solvent is 5 centimeter, right? And for the blue molecules, you will have distance traveled by the compound 3 centimeter, right? So the retention factor for blue molecule will be 0.6, right? And similar like that, you have retention factor for green one, retention factor for the orange, and retention factor for the red. Okay, so the retention factor won't be constant if you keep the same condition for all those elements. Okay, if you keep in the same solvent system, the same absorbent, the same thickness of absorbent, okay, the same amount of material support and the same temperature. Okay, or in another word, the retention factor will be affected by those elements. Okay, if only it can be constant if we keep those conditions. Okay, if we do not change those conditions. Okay. So that is principle of thin layer chromatography using silica. Okay, and in the case if you put the silica gel on the column, okay. So if we have kind of column and you will put the silica gel in this column, so you will have another kind of chromatography. So it also similar principle. It also similar. Okay, so we know that the silica will create the polar interaction, right? So if we have the biomolecule, okay, and with biomolecule it will have the hydrophilic area, right? You have the hydrophilic molecule, right? So you will have hydrophilic area. Okay, so you have somewhere in red with the hydrophilic area, right? So this one resulting in the interaction between silica gel with your biomolecule. Okay, so when you pass the solvent, okay, or the molar biphase go through this column, so the solvent will interfere interaction between biomolecule with the silica gel. Okay, so the molecule will be dissolved, okay, out of the column. Okay, or it will interfere interaction between silica gel and gel biomolecule. Okay, so that we can elute our biomolecule. Okay, so if a chemical function is fixed on a solid support, okay, or we call it a stationary phase with an affinity for this particular function when absorbed, okay. So these interaction can be disrupted by a solvent or mobile phase, right? We has also an other affinity with the stationary phase, right? And the initial molecular support interact will be replaced by new molecule solvent interaction. Okay, so the molecules are dissolved. So that is the principle of the chromatography using silica gel. Okay, so or in another workflows, you can see that if you have the silica gel put on the column, so for the silica it will create the polar interaction. Okay, so for the initial steps, you will make the equilibration with a non-polar solvent. right? It's been passed through here, and then the polar biomolecule will bind to the silica, right? Okay, and when you would like to elute the biomolecule, you will use the nonpolar for the first step. Non-polar molecule are elute in flow through, and when you would like to elute the polar one, you will use the suitable solvent. Okay. So for the absorption of the molecule, you will see it will be affected by the percentage of hydrophilic solvent. Okay, because we know that for the polar molecule, so it will be exhibit the hydrophilic property, right? So of course, the absorption of those biomolecules is will affect by the percentage of hydrophilic solvent which are using. Okay, so for instance, here you will have the elution profile of your molecule when you like to elute your biomolecule sample using the hydrophilic solvent. Okay, in the case if you use a silica gel, right? So at this point, somewhere you will use very low amount of hydrophilic solvent. Okay, because this one it will have the weak comparison power. Okay, electric power, weak electric power. This reason we can consider as the medium electric power. So at this point, you can elute some, and the other point at this point. So it means that you have the very strong interaction between your biomolecule with the silica gel, right? Okay, so it means that you need to increase the percentage of hydrophilic solvent. Okay, so that you can dissolve your biomolecule. If in the case you use silica gel, okay. Or another way to present it, okay. At this point, you will elute up the molecule without any affinity with silica gel. Okay, so this the molecule will go in flow through fraction, right? And at this step, you will dissolve of those molecule with the weak interaction. Okay, so for the next one, you will elute or dissolve a molecule with medium interaction, or for the next point, you will dissolve a molecule with strong interaction. Okay, by using high percentage of hydrophilic solvent. Okay, and you can see that this arrow showing you the orientation of all the solvent which are using for the elution. Okay, for it will increase in the right direction of increase the hydrophilicity. Okay, so you will see the water will be at the highest level. Okay, so remember like that. The weaker one you will have the common one like a hexam. Okay, or the common one with very quite high is the acetylene. It's also common. And then for the strongest, you have water, and then methanol. Okay, so it highly hydrophilic. And also like the other chromatography method, your sample is also normally wouldn't be to be able to detect the presence of your biomolecule. So your system will be connect in a modern system, right? So you have buffer and sample will be loaded on the column using a certain kind of pump. Okay, it means that it will automatically work with a pump system. Okay, the sample or buffer can be loaded on the column here. Okay, and before go to the collector, it will go through an UV detector. Okay, so that you can obtain the elution profile with this kind of detector. Okay, so you know the UV detector normally to detect protein at the wavelength of 280, right? Okay, and when you use the different buffer, right, to create the a certain kind of gradient. Okay, so you see it in the previous slide, you will see that we use solvent to to elute our protein, right? So with this kind of curve, you will see that we use a gradient of hydrophilic solvent, right? Okay, so to adjust and create that gradient, so we will use different solvent. Okay, so for instance, you will have two bottle of the cup of the buffer only, uh, the solvent A, okay, when containing the initial condition, okay, and the solvent B when contain the final condition, okay, and this one, the two bottle can be adjust the concentration before it going to the column. Okay, to create the gradient as we wish. Okay, or it will be pumped to the mixer before go to the column. Okay, for instance, here you have the solvent A and solvent B. Okay, so you will have pump A and then pump B. Okay, so the solution here will be mixed at a plate together, and then it will go to the column. So that reason why in the during the run you can adjust the concentration as you wish. Okay, so it will create a gradient as you obtain in the action profile, like that, right? And because you use the detector, so that reason why you can detect the thing appear during the run. Okay, so that is the application. Oh, sorry, little bit. 1 minute, please. So that is the principle of using silica gels, but the other point, this silica is not very suitable for biological macromolecule. Okay, because with the silica it will exist the polar interaction. Okay, so too much number of polyionic and hydrophobic amino acid, right? So it's if we use the solvent, so maybe it will affect to the characteristic of our biomolecule. Okay, so to avoid that, normally we will use the reverse phase chromatography. Okay, so instead of using normal silica, okay, so because silica will exhibit the polar interaction. Okay, so now we will attack into the silica the small compound to exhibit the non-polar interaction. Okay, so that reason why we call this method is reverse phase chromatography. Okay, so it will be invert, reverse way to elute your compound. Okay, so the separation of the molecule now will based on their non-polar characteristic. Okay, okay. Normally, the silica will exhibit the polar interaction, right? So it means that the polar molecule is will be attached to the silica gel. But now we will grafted the to the silica the non-polar interaction. For instance, you will attack to the silica here the alkene chain. For instance, normally you will use C18. Okay, it means that you will attack here quite long chain of this alkene. Okay, or maybe you will shorten that alkene. The alkene chain is can be only 8 atom of the carbon, or even 4 atom of the carbon. Okay, you can sort the alkene chain. Okay, so you will create the silica gel now with a non-polar interaction. Okay, we wrapped silica with those molecule. So from the previous method, the polar molecule will attack with the silica, right? So now the non-polar molecule will attack here with the alkene chain, right? So it will create this non-polar interaction by grafted silica with alkene chain. Okay, so now for the elution profile. In reverse phase chromatography, we will use also those organic molecules. Okay, we also use the molecule, but now you will see the direction is already reversed, right? So if in the previous method, like water will be the molecule with the strongest the electric power, so now it will be the smallest one. Okay, and the hexane this will become the molecule with the strongest electric power of the solvent in the reverse phase. Okay, so you see the understand the principle of and property of the silica. So in the reverse phase, now you know how it works, right? And actually, for purification of the protein, we can use this one. But for the reverse, some purification of genomic DNA, sometimes you can see that they still use silica gel. Okay, and our DNA will bind to the silica. Okay, and then at the elution step, you will see that they will use water for the elution step. You will see. Okay, but for the protein, it will be the other story. Okay, because the protein it have the other property. It's more complex than DNA. Okay, so they will use can you. Okay, next one. So to elute the biomolecule, so or protein, we can step by step increase the solvent A polarity by using by changing the percentage of the solvent B. Okay, for instance, now if you have a gradient from zero, okay, from zero here to 80% of the B, okay, when you create the Z gradient, so you can obtain this electron profile in red color here, right? You can see the red color, right? The big. So here you will obtain the electron profile with the detector, UV detector, okay? With the at the adsorbent of 280 nanometer, so it means that you have different protein, okay? So you have pick 1, pick 2, 3, 4, and 5, okay? But here when you observe, you can see that pick 3 and 4, okay? So it's nearly overlap acid gradient, okay, from 0 to 80, okay? So here you can see that for the big one, there is nearly no interaction with the silica gel, right? So for this point, it's nearly the weak interaction, okay? And at this point is about medium, and at this place, it means that gel molecule will have strong interaction, okay? Uh, and now we will focus on this point between peak 3 and peak 4, right? So when you make the zoom here, okay, zoom in the peak 3 and peak 4. So we will see that here we can collect different fraction, okay? And if we collect with this gradient, so we will mainly obtain the mixture of the two product, right? So here you have two protein, the first one in blue and the second one in green, right? But here you can see you cannot separate it here. Mostly you will obtain the mixture between the two protein, okay? So how to deal with this problem, okay? So now do you have any idea how to fix with this situation when you have the two protein is like overlap together? You can not separate the two protein like this. Do you have any idea to separate them, make a better separation? Everyone? Oh, sorry. Are you with me?
Yes, I'm still here.
Okay. So do you have any idea to improve the separation in this case? Do you follow me? This one is when well, we are using reverse phase column chromatography, right? And you will use a gradient of the buffer B, okay? When you increase the percentage of buffer B from 0 to 80%, so you will obtain Z elution profile, okay? And problem is that you will see there's an overlap between the two protein at peak 3 and peak 4, right? So now when we make the zoom in of the peak 3 and peak 4, so we can see that we collect mostly the mixture of those two protein, right? So my question is, how you will deal with this situation to get a better separation between the two protein? Stronger one or in an other case, uh, so you mean this one, right? So this the injection or this one will be will have strong intestine, or it will interfere with the non-polar interaction, right? Because in the reverse phase we will separate based on the non-polar one, right? Right. So my question is that when you like to use another solvent, right? So in that case, you will use which one? For instance, now you are using acetone. So your succession will use like isopropanol, the weaker one or the stronger one, or you will use like chloroform, for instance. A and buffer B. Normally, buffer A and buffer B is only different in percentage of a certain solvent. Okay, for instance, if you use methanol, okay, so in the solvent A, it may be 5% of the methanol, and in the buffer B, it will be 100% of buffer B. Okay, do you understand what I mean? So now if in your system, now you are running at a gradient of this buffer. So now in the elution profile, you will obtain the patterns like this, right? If you totally changing the solvent, okay, and you try with as a gradient, so it means that on the elution profile will be changed. Even now, you may not obtain a 5 peak like this. You can obtain like a 4 or 6 peak. Okay, it will be totally different. But you have, sorry, as a way to overcome the overlap between the two peaks. Okay, here's the solution. In this case, you are running with the gradient from 0 to 80, right? So now you will see every peak is elute with an retention time corresponding to a percentage of the buffer B. Okay, for instance, here you will see the peak 3. You see when you do like that, okay, at uh, the top of the big tree, you will make the vertical axis like this, okay, and you will make the horizontal axis to the percentage of the buffer B crossing with the gradient, okay. So you will see that you will have the corresponding percentage of buffer B which are using. Okay, so here's that is the meaning of this sentence. Every peak is allotted with a retention time corresponding to a percentage of electro buffer B. Okay, if you have the big tree with the retention time 1, you also can determine the retention 2 for the peak 4, also like that. Okay, you will make the vertical acid through the top of the peak 4, so it will cross with the gradient curve at this point. Okay, so you will make the horizontal vertical axis here, and you will determine the percentage y percentage of the buffer b we are using. Okay, so now because every peak is elute with a resistance time corresponding to the percentage of the electric buffer. Okay, so now we will change by this way. Oh, sorry, I don't know why this one is not moving. Okay, so now from this point, you will change the gradient. Okay, so from the beginning you can see that gradient here is from 0 to 80, right? So now you will change it. Instead of using z gradient, you will make your gradient flatter. Okay, or you will change a gradient to become more flat. Okay, so in this case, from this point, you will put here, you will see it will be migrate to determine the other retention time. Okay, so that you can determine two different peak. Okay, so you can see the top of the peak will be changed corresponding to the retention time. Okay, or in another word, if you modify, you change the slope of gradient. Okay, so we did not modify the percentage of the b at which the compound is eluted. Okay, so you will see that you still keep the x and y. Okay, but the retention time, now you have retention time 1 prime and retention time 2 prime. Okay, so we just modify the retention time of the compound in the new condition. Okay, you see. So in this case, you see there is only a very small reason it will be overlap together. So for doing the same way, if you make the more flat of the gradient, okay, so the peak 3 and peak 4 is will be more separate. Okay, but sometimes we accept a small amount of the overlap, and then you can ignore this one. You do not collect the mixture between the two, or in the other way, you will increase the you will change, or you can modify the slope of gradient. Okay, and in this case, you will make it more flat. Okay, do you understand what I mean? Right? So now, if we collect, so we will collect about 80 to 90% of a compound as purified. Okay, so when you check with the SDS bed, you will see here's only 100% of the first protein, and at this point, only 100% is the second protein. Okay, and at some elution fraction at the middle, you will observe in the SDS bed the mixture of the two protein. Okay, so that you do not take this fraction. Okay, but for the other case, if you would like to make a better separate, you can change the slope of the gradient. Okay, It's not only for reverse phase chromatography, it's also for the other case. For the other column chromatography also, you will also perform like that. That is the general strategy for get a better separation by changing the slope of gradient. Okay, you know in which direction it you will have a better separation. Is it okay, everyone?
It's okay.
Okay, good. Okay, so you will see here in the dot curve here with the spot, you will see that here's the illusion profile. You can obtain pick 1, 2, 3, 4, and 5. Okay, for the initial condition with the gradient from 0 to 80% of B, right? And then when you change the percentage of buffer B, so now you will see if you use the same sample. So now the pick 1 and pick 2, it will be in the same pick. Okay, and now the pick 3 and pick 4, it will make a better separation. Okay, but here will be in the case you only care about the product of the pick 3 and 4. Okay, you don't care to the protein at the pick 1 and pick 2, so it will become like a overlap and it become one pick. Okay, so you can see that when you change the running condition, the illusion profile is totally changed. Okay, so now pick 5 here is not at this position anymore, it come to this position. Okay, and you can see that when you change the running condition, especially the buffer B, you will obtain the other Ellison volume. Okay, so you see it's totally changes, right? This one is the 1, 2, 3, 4, 5. Okay, so you see now pick have been changed totally. Okay, so for improving the separation in the real case, so you can see that, for instance, in this case, you have some proteins, right? Some sample, right? And they when they changing the gradient for the first image, you will see that the gradient is from 0 for 60. So the peak obtained is neck together, right? Okay, but using the same column, when they change the gradient, only they perform only between 20 to 35. So the peak, you see, it will be totally different. The Ellison volume, Ellison profile is totally different. Okay, so the retention time is also different. Okay, so you see here something is about nearly 10. Okay, so this one is nearly 20 ml. Okay, so with the APLC system, you some of you maybe already used, right? So for the SPLC system, normally you will have the block for the sampler. Okay, so it means that for this kind of block, you can keep your sample in the cool condition. Okay, because especially for some biomolecules, so it requires in the cool condition. Okay. And you also have the next system with pump system. Okay. The pump system will be load your buffer or your sample, okay, to the column, right? And then you will have the UV detector. Okay. So before going to the collector, your sample will go through the UV detector, as I said. And you also have need a computer, okay, for monitoring the running, right? To adjust on uh, the condition as you wish, like percentage of the gradient, flow through, etc. Okay, when you would like to watch, when you would like to elute, okay, you can set up the automatically program, or you can run by manual. Okay. This one SPLC system, is it familiar with you or not? No. Here's an example using FPUC. For instance, you the column ties Atlantic LC18 with the dimensions like that. Okay. So in the mode alpha for buffer A, you win UTFA in water. Or in the buffer B, it will be TFA in acetylene. Okay. And they will make the gradient with the linear gradient at the flow through of 1 ml per minute, and 0 to 30% of the solvent B, and running about 30 minutes, and then they can obtain the separation of a different sample like that. Okay, so they have different molecule 1, 2, 3, 4, 5, like this. The pig is quite nice. So you will have the effect of changing the pH. Okay, so you will know that when you change the pH, it will also affect to the hydrophilicity. Okay, for instance, here at this point you will have maximum hydrophilicity. Okay, maximum one, the at the pH about equal the pi, right? But when you lowering the pH, so it's also reduce the hydrophilicity. Okay, even when you increase the pH above the pi, so you also can reduce the hydrophilicity. Okay, but the link between the silica with C18 chain it will be effect. Okay, or this alkaline chain is sensitive with alkaline condition. Okay, so normally we will not use in the condition of alkaline condition. Okay. So that reason why it will require for aciding mobile phase. Okay. So you will see in the white spot here, it means that you have the silica, right, attacked by the alkaline chain, alkene chain, right? So its molecules will attack somewhere here, right? This one will be the hydrophobic zone, right? And mobile phase you will use it will be two buffer A and B. The difference is will be the difference in water or in acetylene. Okay. acetonichine, okay, and the pH, as we know before, the pH normally we have to use at the acidic acid, pH about 2, okay, because if you increase the pH in the alkaline condition, it will affect the stability of C18, right? And the other HPLC application is also can use for the dissenting solution. Okay, so in the previous part, you already know that you can use side exclusion chromatography or gel filtration to remove zone at the end, right? Protein will be elute first, and then zone will go out later, right? And when you use the reverse phase chromatography, you also can remove the zone, okay? But the order is will be reversed compared to gel filtration, okay? So in this case, in the case you reverse phase chromatography, the zone will elute first in reverse phase chromatography, right? And the less polar element is needed to elute protein later, and other molecule which are retained on the column, okay? So it means that the zone here, it will have the low interaction with the nonpolar part on the silica bit, right? Okay, so now you know that you have a no, actually the third method to remove your zone out of your sample, right? Okay. We all know that the PLC is particularly powerful. It can be used for a peptide, for oligonucleotide, for simple organic molecule. Okay, it's also powerful, but it will be less useful for protein purification, okay, because as you know, it's require the acidic environment, right? So this acidic medium is when effect to the 3D structure of the protein. It will may lead to the denaturing of the protein, okay, or beside that, the compound which are using to elute like acetonichine, this compound is also can be the agent lead to the denaturing of the protein, okay? You understand what I mean? Yes, the
Okay.
APLC, okay, is suitable for the peptide, small peptide, oligonucleotide, and organic molecule. So that reason why for this APLC. So remember that APLC system is the principle is based on the reverse phase. Okay, and I already remind you that for the reverse phase, your silica gel is attacked with the amkin chain, right? And the elution based on the hydrophobic city, right? But for the origin of silica gel, so it will based on the polar property. It means that the elution will based on the hydrophilic city. Okay, so in some application like in purification of DNA or plasmid, sometimes they also use the silica gel. Okay, or okay. Uh, So we can make that the HPLC is the powerful system, but it's less useful for protein purification because this can be resulting in the denaturing of the protein. Okay, so different reverse HPLC column capacity. So you will have a kind of capillary, okay, with the certain dimension 0.32 millimeter, and you can have a small analytical column with the length of 46, or the bigger one you have semi-preparative with the resistant the fee of 10 millimeter, or the preparative with the big size 20 millimeter, the for the dimension of the column. Okay, and with different type of column capacity. So you have a capillary, you will have depth volume, the flow rate, and the change in milligram. Okay, for the analytical, semi-preparative, and preparative. So each type of a column will be suitable for the sample volume we would like to use. Okay, and from analytical to preparative and vice versa. So we have the way to save it. Okay, for instance, you will have a scale factor for assessment of flow rate and column chain. Okay, for instance, you will have L1, and R1 is length and radius of initial column. Okay, and L2 and R2 is length and radius respectively of the new column. Okay, and the X here stand for the scale factor of assessment flow rate, and the column chain is when we calculate as this formulation depend on the length and radius of the initial and the new column. Okay, so that you can shift between the analytical and preparative column, or reverse way. Okay. Okay, this one is will be specific. So you also have example for the different profile which is obtained from different reverse HPLC column capacity. Okay, for instance, on the left you will have the Edison profile when you use the column. If you load only 1 milligram of the sample. Okay, now specifically with this kind of a column. Okay, and if we load 10 times of the amount of sample, so you will see the peak here is sometimes it's going to reduce the resolution of our Edison profile. Okay, so of course it will affect to the resolution if you do not choose the suitable column. Okay, so that reason why we have to shift between column system. Okay, shift from analytical column to the preparative one. So the parameter related to the separation quality in chromatography. So you will see there's many different element effect to the the separation quality during the purification. So the resolution R will be calculated by this equation. So you will see that here's the elution profile you can obtain, and you will have the two molecules of the protein A and protein B, right? And you have the elution volume of the molecule A, elution volume of molecule B, y of the side, the width of the first peak for for molecules A, and this is y of the peak for the protein B. Okay, and you have a half of y of molecule A, a half of y of the molecule B. Okay, you also have the V0, VT, okay, depth volume and the total volume. Okay, so you still remember, and the resolution will be divided by the VB minus VA, divided by the WA plus WB divided by 2. Okay, so the separation quality in purification, especially in our column chromatography, is when effect to the efficiency, capacity, and selectivity. Okay, then this one also can be calculated by different equation, and it can affect by different element. Okay, and in general it will affect to the resolution, or affect to the separation quality of our purification. For instance, with the first element for the efficiency, the measurement of the peak wise and more peak sharp, it will be better. So it will be it will be evident for the better separation. So we will prefer the peak like the sharp peak like that. So it will tell us that we will obtain the high efficiency, and for the low peak like that, we will obtain kind of low efficiency, right? Okay, so for the Ellison profiles, with the Ellison profile, so we can evaluate out efficiency of purification. Okay, so it will be very useful if we have a modern system like a HPLC system, right? Okay, so this one is will be the equation. Okay, so we can jump to that. So for the capacity, you also have the equation to evaluate that. But in general, so okay, so we have the selectivity of the efficiency. Okay, when you obtain the elution profile like that, it means you have the good selectivity and also the high efficiency, right? Good selectivity, and with the spot like that, you have the good selectivity but the low efficiency. Okay, and when you have some kind of overlap, a peak like that, it means that you have the low selectivity. Okay, and if you have the Ellison profile, the curve like that, it means that it have both low selectivity and low efficiency also. So the one we would like to obtain is this pattern, not the other one. Okay, the good selectivity and the high efficiency. Okay, so beside HPLC, okay, HPLC stands for high performance liquid chromatography. Okay, so in order to improve the separation quality, so they can create, they can improve, they can develop a system called unchar performance liquid chromatography. Okay, UPLC. Okay, only different in the U. One, the previous one we have high, right, and this one is unchar. Okay, so by creating and develop synthesized of chemistry of equity, so they develop this kind of particle for UPLC. Okay, so the structure is could be like this. Okay, vice versa. So depend on of the size of the particle for the UPLC. So it also have a different kind of column. Depend on the size. Like here you have a 10 micrometer or less than 2 micrometer. Okay, this scheme show you the improving of resolution for here, for instance, here you have the HPLC one, so the curve is the side with the 10 micrometer particle is only provide a curve like that. When you the smaller particles, so you will get the better resolution. Okay, or here when you use the LC, and you can compare with the HPLC. Okay, for instance, for the same sample. Okay, so you will see at the point have been circled with a green color, the red and black. If in HPLC system, you only can obtain this pattern. So in UPLC system, you can see here the profile is very different. This one in the red region also, or in Z region also. So you will see that the profile for the UPLC is will be better. Okay, so the resolution is will be better, right? It's really improve the resolution in UPLC instead of HPLC. Okay, but the principle is also the same. Or for the other Ellison profile, so you can see that when you use the same radius or column, but it's also a little bit different in length, but even. So here you also can see that it will affect to the running time. Okay, so for instance here the time for the running is about 20 minutes. Okay, so when you use the HPLC system, so the column is longer. Okay, it's 100 millimeter double compared to the HPLC. So the time for this HPLC column is also double, 40 minutes. Okay, and in the for the separation, you also get a better resolution for the UPLC. Okay, so that is the advantage of a UPLC compared to the HPLC, and it has been developed later. Okay, so that is the SPLC system based on reverse phase chromatography. Okay, and UPSLC system. Okay, so for the next one, the next chromatographic purification method, so we will work with ion exchange chromatography. Okay, this one is also very important. in the in your paper, I don't remember if they use this method or not. You will see. But normally they wouldn't use very common with affinity chromatography. That is the most considered as the most simple one and common one. So if we do not, okay, so we will see for the next class. But I let it at the end. Okay. Uh, for job filtration is very important. Column chromatography, so we have done with that. Okay, reverse phase. Okay, so now is the third column chromatography, ion exchange chromatography. Okay, so this one you know that is the principle of separation of molecules is based on their charges. Okay, right? In the reverse phase, mostly the principle is win based on what the organic group in which inhibit the hydrophobic characteristic, right? So now you will have the methods based on the residue in which exhibit the charges group, right? So chromatographic process based on the track of molecule to be separate. We have ion exchange. Okay, so the ion exchange is a compound usually porous, wrapped covalently with a chemical group. Okay, as a cationic or ionic. Okay, so that reason why we have ionic and cationic. Okay, so normally you will have a certain kind of compound to form the bead here. Okay, and then this special compound will be usually form the porous, and then it will be wrapped covalently with a chemical group as a cationic or anionic or cationic. Okay, so it will resulting in the interaction with the negative charge or positive charge protein, right? So this the experiment is usually performed in 3 steps. The material loading on the column based on the charge of the molecule and of the resin. Okay, and then the elution of molecule usually by increasing gradually the ionic force of the eluting solvent. Okay, so the same principle for general column chromatography. And then the next step, the column regeneration by extensive wash with a solution at a pH, allowing the formation of the charts as they were initially. Okay, it's not so difficult. So for the solid matrix can be used will be the dextran, the polyacrylamide, cellulose, okay, and those composition will be will form a kind of porous, okay, and this kind of porous, this kind of bit also wrapped or linked with the uh, acid group negatively charges. Okay, or in this case, so we will have kind of cation exchange. Okay, because you have the negatively charged molecule when by with the the speed, right? So your protein suspect to have negative charge. Okay, so in this case we will have kind of cation exchange. Okay, so the biomolecule are the positive charge. Protein will have a global positive charge if the buffer pH is below their pi. Okay, isoelectric point pH. For the ion exchange in general, we have to pay attention to the pH of the buffer used. Okay, otherwise you cannot buy your protein to the column. Okay, right? So for cation exchange, so normally you will have different of negative group will be routed to the bit here. For instance, you will have the sulfoborine or carboxymethane. Okay, this one is a little bit weak binding, and sulfoporine is very commonly used. It have a very strong binding to the bit here. Okay, so it depends on kind of column. So you will see the characteristic of that column. And if you have the solid matrix of dextrans or polyacrylamide or cellular will be grafted with an cation group positively charged. Okay, so you will have kind of anion exchange. It means that the biomolecules are those negatively charged. Okay, protein will have global negative charge if the buffer pH are above the pi. Okay, it will be in the invert way compared to the cation exchange, right? Okay, so here for in the case of anion exchange, you will have the bit can be the dextran, polyacrylamide, etc. Right? Then it will be wrapped with the different molecule here. We will have the molecule will provide very strong interaction like this complex molecule or trimethylene ammonium. Okay, this one is also to provide a strong interaction, or the weak one like amino 18 or the 18 amino 18 DEAE. Okay, that is the common molecule used in anion exchange. Okay, and you also know that for our separate amino acid, it also have its own pK for the side chain, right? Here's different example of amino acid residue. Okay, so you have the alpha amino pKa is about this value 6.8 to 7.9, and for the alpha carboxyl pKa is about like acidic acid around 4. Okay, so it's really different. So it will absolutely the buffer will affect to the status of our protein. If we put it in the acidic or alkaline condition, this one you already know. So for the cation exchange, normally you won't use the pH smaller than the pi, and for anion exchange you will use the buffer with the pH in the alkaline condition or the pH above the pi. Okay, because the for cation exchange your protein supposed to be positive charge. Okay, the final net charge is the negative positive one, and for the anion exchange is the invert way. Okay, So now you have the protein A, the pi equal 9. Okay. When you use the can you use the buffer 7 or not? Okay. The buffer pH is far below pi. Okay, it's quite far, right? So protein would rather be strongly positive charge, right? So in this case, if you the pi is 9 and you use the buffer about 7, so the protein will rather be strongly positive charge, right? So the protein A will bind identical lead on a weak or strong cation exchange column, right? Right. So we will can choose the weak one if the buffer is far from the 7. And if you have the protein B, the pi is about 7.5, for instance. Okay. So if we use buffer pH about 7, so in this case, the buffer pH is just below the pi, right? So the protein will rather be weakly positive charge, right? So in this case, protein B will bind strongly only on a strong cation exchange. Okay, so in this case, we will choose a strong one. Okay, strong column. Okay, because in the previous one you have different kind of group when a molecule will be grouped on the column. Okay, so that reason why you have a different option. In that case, for instance, in the first case, you can use the weak one, but in the second case, you must choose a strong one. In the first case, of course, you can use both weak and strong, but in the second case, the strong one will be sufficient. Okay. And during the purification step using ion exchange, you have to consider the different element. So we have determined the optimal pH. Okay, of course, this is very important. You have to determine the salt concentration for the binding and the adhesion. Okay, so for the binding, of course, you have lowering the salt concentration. Okay, to avoiding the interfere of the binding between protein and your column. Okay, and the last one is to determine of the resin capacity. Okay, because of the characteristic of the resin is also a cost effect to the efficiency of the running. So that is the element must be considered during ion exchange. Okay, so to determine the optimal pH. So example that you have 1 milligram of the resin per tube. Okay, you have the ion exchange resin and then you will put on the tube, right? So you will make the equilibrate with the pH from 5 to 9 for anion exchange, 4 to 8 for cation exchange with an 0.5 molar buffer resolution. Okay, buffer will be added to the ion exchange resin, right? At the different pH, right? So here the buffer have been added at different pH. Then protein mixture here will be loaded in the column. Okay, so protein will be now in the solution. Okay, so now you will see that protein will be bind to the resin. Okay, so you will decide the choice, the pH about more than 6.2. Okay, so because in this case you will see that protein will bind with the resin. Okay, but in this pH it not bind to the resin. Okay, so we have determined the suitable pH range. Okay, so to determine the salt concentration, okay, we need to adjust the concentration to the desired concentration. Okay, so for the binding and for the elution also. Okay, so we also perform the experiment like that. We adjust the salt concentration. Okay, and then we will see that the choice for the salt concentration will about below the point 0.17 millimole for the binding. Okay, and the choice for the salt concentration for eluting will be about 0.3. Okay, so you will see at this point we can make the eluting. Okay, and at the low concentration it will be for the binding. Okay, that is the second element you have to determine. The first one is pH, the second one is salt concentration. Okay, and the last one is will be determine the resin capacity. We will determine the resin capacity. Okay, for instance, here you will prepare a different range of sample, right? From 10 to 100 milligram per ml. Okay, then you will decide the choice for protein is only below 40 milligram per ml. Okay, because if you put a lot of protein, so it will be overload, right? So it cannot bind effectively to your column. Okay, so that reason why you have to know the limitation of the amount of the quantity you need put to the column. Okay, so after you determine of all the element pH, salt concentration for the binding and elution, determination of the resin capacity. Okay, so in our example we have 100 milligram of resin per tube. So the equilibration, the pH from this pH condition buffer solution at 0.5 molar, and then after we assess the desired salt concentration, so we will make it for 5 to 10 minutes, and you will allow the resin to fall down in the tube, and you will test the activity and presence of the protein in the supernatant. Okay, it's all general protocol for the testing for both pH, salt, and the capacity. Okay, so that we can figure out at which condition it will be suitable for our experiment. Okay, and that is the point we need to be considered for ion exchange. Okay, and you should remember that during the a slide concerning the Ellison profile reverse phase. Okay, it's also the same strategy. If you for the Ellison, if you would like to separate your protein using ion chromatography. Okay, if in reverse phase you have to use different kind of solvent for elution. So here to elute your protein using ion chromatography, you have to change the salt concentration. Okay, so that you also can change the gradient of salt concentration, and you can also change the slope of salt concentration to make a better separation. Okay, do you understand what I mean? The principle of ion exchange and the step of our own chromatography process is also somehow the same, right? And for the ion exchange, I'm not remind use for instance here the thing I remind you here is the how to make okay as a step. Okay, this one. To be able to control your purification step, you must understand the principle, okay, and how to make a good elution, right? So for a certain condition and for certain method, you have of course different strategy to collect to separate your sample, and at a certain condition you will obtain a certain profile. Okay, so if in the reverse phase, right, you increase the percentage of certain solvent, right, to create a certain gradient here, okay, so that you can separate your protein. For instance, in this case, if you run an ion exchange, okay, you will use the salt concentration to elute your protein instead of increase the percentage of your solvent. Okay, here's the in the ion exchange is you will increase the percentage of salt, right? Because the salt will interfere. The salt will interfere the interaction between the protein with anion or cation bit, right? And to make a better separation, for instance, in the case you have also like gradient of the salt between 0 from 80% of the salt, okay, and then you also obtain the peak 3 and peak 4 like that, and the same strategy you will apply is to separate the two peak is to make to modify the slope of the gradient. Okay, got it? And even in the affinity chromatography, it's also the same strategy. Okay, so this one, those slides very important. It's also general for those column chromatography. Okay, do you understand what I mean?
Yes.
Yes.
Okay. So today we have finished the lecture with geofiltration, reverse phase, and ion exchange. Okay. So for the remaining one, let's see. We have what? We have affinity. The one is important, but it also